Welcome to my session. My name is Guozhang Wang. I'm an engineer and the tech lead of the streams team at Confluent. Today, I'm going to talk about Kafka streams, stream processing made simple with Kafka. Before I start, can I know how many of you have heard about Kafka? Raise your hand. Great. And how many of you have used Kafka? Wow, that's great. Thank you. And OK, so let me start my talk by asking this question first. What is not stream processing? OK? You may have heard before that stream processing is usually transient, it's approximate, sometimes it's even lossy. So if you really want to have a stronger guarantee for your computational logic, think twice compared with using a batch processing models. And now I want to claim that this is not actually the case for stream processing. And in my definition, stream processing is just a new programming paradigm to code your applications, where your inputs is just an ordered series of data, and your computation is continuous instead of batch-oriented. And to illustrate my idea, I will review some of the existing programming models besides stream processing. The first model is request and response. This is a very simple model, and it's purely synchronous. You have one input at a time read as a request. You send to your service, and you wait until the output as the response is returned to you. But in order to scale such a programming model, you basically need to add more and more services in order to handle the increased traffic of the requests and responses. The second model, which I would say on the very other end of the spectrum, is batch processing. And I hope that this processing model is more familiar even with request and response, because after all, this is a Hadoop conference, isn't it? And in batch processing, you have a nice decoupling of the data generation with the data computation, where you batch your inputs as a bounded data set, and you submit it into your computation. And after a while, all your outputs will be visible. So in this case, because of the nice decoupling, you actually have more flexibility to scale your services to have better throughput, with the cost that you may actually pay more latency because the time difference from where you have collected enough data for processing from where the data was originally generated may be different. And now, stream processing. I would claim that it is actually somewhere in between of those two extremes, where it is also asynchronous compared with request and response, but not like the batch processing, where you send your data to your computation. Stream processing actually models your inputs as series of data sets and apply the computation continuously to generate outputs whenever they are available. So it actually brings your computation closer to your data. And although we have seen several systems that is designed for stream processing in a way of approximate computation, I would again emphasize that this is not necessarily the essence of the programming paradigm itself. Okay? And part of this misconception, I think, is because of this implicit trade-off between latency, cost, and correctness. And some systems may have just been designed to optimize some of those dimensions instead of actually leaving users the flexibility to make their own trade-offs. And actually, this flexibility is very important today for stream processing, because we actually have seen a lot of different applications having various preferences for those trade-offs. For example, if you are just building a real-time billing services, right, then you may actually care about your correctness so much that you would love to trade some of your latencies. But if you are actually just building a log processing system, you may not be really willing to trade those, make those trade-offs. And on the other hand, if you, for example, building a ETL services, then you may not care so much about latency. But let's say if you're building a real-time alerting and monitoring systems, you actually may care a lot about your latencies. So a quick summary. And again, if you can leave my talk with just 2 takeaways, I hope this one should be really one of it. That stream processing is not necessarily approximate or lossy or anything. It's just a new programming paradigm where instead of sending your data to your computation, it just brings your computation nearer to your data for continuous processing. And in such a model, it's actually very important to allow users to make trade-off decisions among latency, cost, and correctness. So that's all about the first question. But my talk actually have two keywords, right? Stream processing and Kafka. So where is Kafka in this big picture of stream processing? Well, in stream processing, a very common pattern for developing application is that you will actually put your data from your data generator into an ordered queue, so that the data generator do not actually need to wait for the data to be processed, but can just proceed themselves. This is what we call the decoupling of the data generation to the data computation. And then another separate process can then fetch from this ordered queue to get their data and compute the results in real time. If you look around in the open source world, you may find that actually the most common place today to implement such a queue is Kafka. And there are a couple of benefits actually to use Kafka in this as a centralized data pipeline. One is that inside Kafka, you have this natural logical ordering of all the data you are piping in and out of the system. And second is that all the data you stored with Kafka is actually persistent. And now this is actually very important because this feature allows you to do all kinds of things very easily. For example, reprocessing or pressure handling, back pressure handling. Like assuming that you have a peak time and your consuming and processing rate cannot catch up with your data producing rate. So with Kafka, you don't really need to worry that the data will be dropped because it will just be persisted in the brokers. And then later on, when your consumption catch up, you can actually reprocess those data. So all of those benefits makes Kafka a really good fit as a centralized data pipeline system for your real-time data streams. And the next question is, now assuming you have all your real-time data in Kafka as data streams, how would you process them? There are a couple of common practices already, and I will summarize them here. The first option, which I will call it the DIY option, is that you just build your own applications. You can actually use a lower-level client, such as a consumer, to continuously fetch data from Kafka, and you do some processing on your own, and eventually you can send the results either back to Kafka or into some external services to store them, such as Cassandra, Elasticsearch, Hive, whatever. But the caveat of this DIY approach is that stream processing is not easy, right? You actually have to consider a lot of different characteristics, such as ordering of your data, partitioning and scalability. How would you handle states in your processing application? How would you handle out-of-ordering data in your window operators, et cetera, and et cetera? So a second common approach is to leverage a fully fledged stream processing frameworks, right? And you have basically seen examples like Storm, Spark Streaming, Flink, and Samza, and much more. And all of those frameworks gives you this abstraction to basically hide a lot of the low-level details, such as data parallelism and fault tolerance, so that the developers can actually focus on their computational logic. Now, this is actually a very good approach. But once you have decided to deploy applications, one thing you realize is that before you actually start your computation, you need to first set up your cluster by installing all those kind of runtimes into the cluster, and then you can submit your application like a job into your runtime. Now, I'm not saying this is actually not a good solution. What I'm saying is that if you already have, say, a Spark cluster or Yarn, then actually it will be a natural fit for you to use, say, Spark Streaming to do ETL, or use Samza, which is using Yarn for its resource management. But the question is that if you try out different of those runtimes, you may find that they have their own systems to do all kinds of different things, such as configurations, resource management, scheduling. You can think of, you can name it, right? And one common question is that if I already have my own software stack, like I use Docker or I use AWS, can I actually easily apply my existing tools for all those kind of different things? So here is a third approach that I'm going to propose here, which is to have a lightweight stream processing library that it does not have any extra dependencies, hence no operational cost enforced. And you can just code your applications using the library and deploy it in any way that you like, right? And Kafka Streams is just this kind of stream library that we have just included in the Apache Kafka open source project since the 010 release, which is just over a month ago. It is a library, but also with very powerful features to allow you to code very different and complex stream processing applications. For example, it supports like event-at-a-time processing and the stateful processing management. And also, it allows you to reason about this notion of time in your windowing operators, and also highly scalable and distributed and fault-tolerant, etc. You can actually code your applications using the Kafka Streams library and deploy it anywhere, all the way from a single laptop into a data cluster in your data center. And all you need to do is just to include this Kafka Streams library package into your application. And then use whatever your favorite tools to do resource isolation, configuration varying, all kinds of things. By the way, a disclaimer here that this spectrum of coolness versus uncoolness is purely based on the personal preference of my PM, Michael Null. So if you disagree with Spectrum, come to me and I can give you his Twitter account. The design principle of the Kafka Streams library, again, here is that we want everything to be simple, because we believe that simple is beautiful. With a simple approach of a lightweight library, you can have the flexibility to build up your own software stack using your own tools for each layer of your softwares. And now let me just quickly go through some of the APIs in the Kafka Streams library. This is example code I use for using the Streams DSL API to code a stream application. And in fact, in Kafka Streams library, we have two sets of different APIs. And Streams DSL is a higher level API. We have also a lower level processor API, which is very similar to the Storm, Spout and Bolt APIs, which I will not touch upon due to the time limit. So in the Streams DSL, you start your application by always creating some input streams from one or multiple Kafka topics. You can then apply different given operators to transform your streams, such as joins, aggregations, as simple as filters and mappings, to create new streams or tables. And eventually, you can pipe your result streams or tables back into Kafka with a specific topic. And after you have specified such a computational pattern, you can then create a Kafka Stream client and given this computation as well as your configurations into the Kafka client and run it. And a few words about the configuration here. Inside the Kafka Streams, you can not only specify the stream-specific configuration, such as your application ID, your Bootstrap server list for your Kafka Streams client to talk to, but also you can specify properties for your lower-level clients, such as your consumer and producer clients. For example, if you want to use the security feature, which is installed since the 09 release of Kafka, to authenticate your access to the Kafka brokers, you can simply just pass the corresponding properties to this stream config, which then will be propagated to the lower-level interfaces so that you can automatically inherit your security feature into the Kafka broker, into the Kafka clients. But that is all I want to talk about APIs, because we all know that when you are evaluating a programming framework or library, the API is usually just a small fraction of the whole evaluation. Once you start using it, you will find actually the most pain point is how you can operate your application and how you can do debugging. And again, here we believe that simple is beautiful. And for the rest of my talk, I will focus on how this Kafka Stream library can make all those things simple for you. First of all, the key idea of the Kafka Stream library is that we will leverage fully the underlying Kafka clients as well as the brokers to tackle a different set of hard problems, such as data partitioning. And for those of you who may not be familiar with Kafka, I will do a very quick overview of Kafka key concepts. So in the Kafka brokers, your data is managed as immutable messages, which is appended into this append-only log. Producers always send data to Kafka, and which is appended to the tail of your log, where consumers can start at an arbitrary position in your log specified by this logical offset of your message, and then start sequentially reading your data from that position. And in order to achieve data parallelism in Kafka brokers, we can actually group logs into topics and further partition your topics into multiple shards, or what we call partitions, which can then be hosted on different broker machines. Then your producer and consumer clients can talk to different broker machines, producing and consuming to different topics. So that's it about Kafka. Now I will talk about the key concepts in Kafka streams. Inside Kafka stream, we model each stream as an ordered series of key value pairs, where each key value pair is defined as a record. So mapping back to the Kafka concepts, you can see that the record here can potentially be corresponding to a message in your Kafka logs. And application logic is specified as a graph, which are connected by the streams. And each connected node in here in the graph is called a processor, is called a stream processor. And each stream processor takes one or more streams as its input and generate output streams to its downstream processors. So going back to the examples I just showed you, when you are actually creating the source streams and you are transforming them into new streams, you can actually constructing this graph of processor topology by defining different processor nodes connected by this stream. And there are two special kinds of processors in this topology. One is called the source processor. The source processor does not take any input streams, but only generate output streams. It is used to fetch data from the Kafka logs and generate the source streams for the downstream processors. And on the opposite way, the sync processor only takes input streams but does not generate any output stream anymore, because all it does is to just pipe the received records from the input stream back into the Kafka logs. So when you have this topology in your Kafka Streams client, and you start executing this client, the source processor will continuously fetch data from the specified Kafka topic partitions. The records will then be passed throughout the topology all the way to the sync processor, which then will be piped back into other Kafka topics partitions. And also, when you want to achieve data parallelism, all you need to do is to just start multiple instances of this same written piece of code using the Kafka Streams library. And the multiple instances can then distribute the work among themselves so that each instance will basically start their own replica of the topology and process a non-overlapping subset of the input topic partitions. So that's some basics I want to talk about Kafka Streams. Now let's move on to some fancier features. The first one is state management in a stream processing application. If you remember all the given operators in a high-level stream DSL, you may find that actually they can be grouped into two different categories, right? The first category, I call it the stateless operators, like filter and map. In those operators, you take one stream as your input, and each processing of the record is independent. You process one record as input, and you generate one output. And for another category, which I call it the stateful operators, such as joins and aggregations, the processing of the records is not independent in the way that you actually may need to access some recently reviewed, some recently received records, as well as some derived records in order to process an incoming record from your input stream. And for those stateful operators, you really need to have like a state store to basically store your recently received and derived messages. There are two common places to handle a state store in a stream processing application. One option is that you will have an external or remote state store, which is shared among all your instances of your applications. And whenever you basically need to query the state store or update the state store, you make a remote call to the storage, and then you get your response back. But of course, doing that, you actually will pay more latency because of the remote IOs. A better solution, that I think, is actually to have this local state. where you have your storage just to be co-located with your processing instance. And each of the instances will have its own partition of the state stores, which gives you faster processing time and have a better isolation. And so concrete to the Kafka Streams library, what we achieve here is that for those stateful operators, such as aggregations, the library will automatically create a local state store that is accessible by your, say, aggregator operator here. And when you have multiple of your instances, each instance will have its own state stores co-located with itself. And remember, because Kafka Stream instance will only process a non-overlapping subset of your input topic partitions, each of one of your local state stores is actually representing a shard of your global view of the state store. Another concept in stream processing is time. And I think that time is very important in stream processing compared with batch processing, because the ability to reason about time actually is crucial when you can actually handle varying time skews in your input streams. And two common concepts of time is event time and processing time. The event time is when your input records are generated and are sent to your centralized pipeline, which is, for example, here, Kafka. Whereas your processing time is when these records really have been fetched into your processor and being computed. So in the ideal world, you will hope that your event time will be very likely to be your processing time. But in practice, they may actually be quite different. And what makes worse is that sometimes the ordering of your stream time and your processing time can actually be out of order. And I use an example of Star Wars films to give you this illustration. So here, imagine that your event time indicates the ordering of each movie story happening in the movie world. And your processing time is actually the year when that story was actually filmed. You can see that your processing time is actually out of order, really comparing with your event time. So when you are computing or when you are processing your streams, these out-of-order scenarios really need to be taken care of. And in Kafka Streams, the way we handle such scenarios is to associate a timestamp to each of the records in your streams. And the users can implement a so-called timestamp extractor to define the timestamp for each one of your input records. You can, for example, use the word clock time to define your notion of time as processing time, or you can basically just extract your timestamp from the payload of your record to define it as your event time. And why is that different? Why is that important? One example is in the windowing operator, right? Suppose that you have a running windowing aggregation where each of your window is basically computing some running statistics for that window bucket. And here I use different color for indicating the different timestamps of your records. Now suppose you have actually a new record coming, which is indicating to a very future timestamp in your time span. What you need to do is actually creating the corresponding bucket of this window for a future bucket so that they can be correctly calculated. And similarly, while you are continuously processing your records and building your buckets for your statistics in your windows, you may also have a late arrival record, where here you can actually have a record which is corresponding to a very old timestamp in your windowing. And then you basically actually need to find the corresponding bucket and update your corresponding statistics. So having this notion of time helps you to basically handle the out-of-ordering and time skewness so that you can still have the correctness answer in your different operations, such as windowing operations. OK, so I have talked about state management and time and window operators. The next thing I'm going to talk about is fault tolerance and reprocessing. But before that, let me switch my gears and talk a little bit about the one feature that is introduced in the Kafka Streams DSL. So when you are looking at this example I just showed you before, you may find that we have two types of streams here, or two types of classes. One is the K stream, and one is a K table. And why is that? This actually is coming from an observation that we are making while we design the Kafka stream library, that actually in stream processing, tables and streams are interchangeable. I will give you a very concrete example to illustrate this idea. Now suppose you have a stream of key value records where each of the records is treated as an insertion into your destination table. So that by replaying such a stream, you actually can get different snapshots of your destination table, depending on which position you have been replaying your insertion streams into. So basically, from a stream, you can reconstruct your destination table. And similarly, if you just have the ever-evolving table, which is basically updating its own key value pairs or inserting new records, and you capture each of the record as an entry into your constructed stream, you can also reconstruct your stream from this evolving table as well. So basically, given any one of those two concepts, you can always reconstruct the other by replaying either the stream or by capturing the data changes from your table. And I call it the stream table duality. So again, the summary is that you can actually treat a stream just as a change log or commit log of your table, and you can actually treat your table as a running materialized view of your stream. One concrete example is you can think of like the changelog capture features in a RDBMS. So based on that observation, we have actually defined two different kinds of streams in the Kafka stream library. The first type is called the K-stream, where each key value pair is treated as a normal record. You can think about it as like a pen only into your streams. So examples of such a stream can be like a series of credit transactions, or page view events, or your server log entries, right? So each record is independent. It's just the normal key value pair. And another kind of stream, I call it the K-table stream, where each record here can be treated as an update to your materialized tables, so that each record can be treated as an overwrite of the previous record with the same key. So just to illustrate a bit more about this concept, assuming we have two different kinds of streams. The first is a K-stream that is illustrating a user purchase history. And the second stream is basically a K-table stream illustrating a ever-updating user employment profile. When you are playing those two streams or processing them at a given time, for example here, you can interpret the first stream as that Alice has bought X, and Alice is now working at LinkedIn. But when you see a new record from the same key, Alice, in a K-stream, you actually will interpret it as that Alice has bought eggs and milk. Whereas in a K-table stream, you will actually interpret it as that Alice is now no longer working at LinkedIn, but Microsoft. And because of the semantics difference, when you apply different aggregation operators, for example, they may also give you different results. Here, I give you another example where the values now are just integers. And depending on how we are going to construct this stream as either a K-stream stream or K-table stream, their aggregation results will be different. For example, here, when we see a new record of Alice with the new value 3, if it's a K-stream.aggregate, it will give you an updated value of 5, which is a sum of 2 and 3. But if you're considering this stream as a K-table stream, because the new record is actually overriding the old record in your stream, you will actually get your aggregate results as 3 overriding 2 instead of 3 summing 2. And in the library DSL, we actually have different kinds of operators for you to basically transform a stream to a K-stream to a K-table or a K-table to a K-stream. For example, all the aggregation operators will always result in a K-table to you. Now, why is that important? This is very important because you can now actually code your applications using Kafka streams just as a distributed and embedded database, and using the data locality to actually handle your updates to this database tables. So for example, still we have this running joins and followed by aggregations, and aggregation have a local state associated with that operator. Suppose now you have a new record coming from one of the joining streams, stream number 2, and it has the same key as the first record in this stream, which is red, for example. This will actually result in a new record in your joining stream from the joining processor. And this stream will be piped into the downstream processor, which is this aggregation processor. The aggregation processor will update the state stores and also generate an update into the resulted K-table stream. But here, this K-table stream new record will actually override the newer record, which is the first record in red here, because in here, the K-table semantics is different, where you have this new record overriding the old record. So now with this semantics, it actually will become very easy to handle the fault-tolerant scenarios in Kafka streams. So remember, we have this duality between a table and a stream, or a state store with a stream. So we can now actually using, again, the Kafka topics to basically back our state updates into, say, a special topic. And let's say this special topic is called the changelog topic. And if you are familiar with the databases, you can think of this changelog topic as a write-ahead log. So whenever you have updates to your state stores from, say, an aggregation or a join operator, you will also write a new record as a change into these changelog topics in Kafka. So then, for example, in a case of a failure in one of your instances, again, Kafka library will automatically redo the distribution so that all the computation, processing, and the states will be migrated into another existing instance. And by just replaying the changelog topic partitions from the Kafka logs, you can actually restore your states and then restart your computation for this specific processing task and the local state store again. And then similarly for reprocessing your application. Now suppose you have an application where you find a bug so that you want to rewind into an older history in your streams and restart. Or you just want to upgrade your application logic by doing a rolling bounce. With such a duality, it actually becomes very easy because all you need to do is to restart a fresh new state stores and rewind your offsets to your old history in the old history streams. And by replaying the streams and updating your stores, you will eventually catch up with whatever you have stopped. And then you can do the switch to basically complete this reprocessing story. So now those are all the important features I want to cover for Kafka streams today. But again, one thing I want to emphasize is that we want to make all those powerful features easy to use. Because if a feature is not simple to use, it is really not that useful. OK, now you may ask me, I like Kafka Stream Library, and I like using it for my stream processing applications. But I don't have my data in Kafka yet. How can I make them in Kafka so that it can be processed using my Kafka Stream Library? In the 09 release, we actually have a new tool called Kafka Connect, which is a framework that allows you to basically ingress and egress your different data into Kafka and out of Kafka. And it has actually become a very big community effort. We have already more than 30 connectors contributed from the community from, say, MySQL, HDFS, Cassandra, Elasticsearch, all those different connectors following this Kafka Connect framework to basically allows you to use the connector to pipe data in and out of Kafka. And with this tool and Kafka streams, you can really make Kafka your centralized real-time data stream pipeline, where you use Kafka Connect to pipe all your applications and the data stream and the database changelogs, for example, into Kafka as your stream data. And you use Kafka streams or some other your favorite stream processing frameworks to do the real-time applications or real-time analytics. And then eventually, you use Kafka Connect again to pipe your results into your offline systems, like a Hadoop cluster or a data warehousing systems. OK, so that is the end of my talk. And here, again, I have two takeaways for you. One is that stream processing is not necessarily lossy. It's just the new programming paradigm for you to code your applications, where you can bring your computation nearer to your data. And with Kafka streams, you can actually make this task much easier with your stream data in Kafka. And if you don't remember those two takeaways, I will grab you and run my slides with you again. If you want to learn more about Kafka, just download Kafka streams from Apache open source and play with it. And we also have a joint booth with ThinkSoft today until Thursday. We have live demos on Thursday, so that you can also pay a visit to our booth. And with that, I want to thank you, and that's it. Oh, by the way, Confluent is hiring. So if you are interested in working on Kafka-related problems or anything that is real-time, come to talk to me. Thank you. Any questions? So the question is, how can I achieve exactly once with Kafka Streams library? This is a very good question, and that's why you make backup sites. So exactly once is actually ongoing work in the Kafka streams. And actually, for here, we want to actually achieve the end-to-end exactly once semantics. It means that you actually have your data from, say, your MySQL bin log, and you pipe it into Kafka, and you process it with Kafka streams, and eventually you send it back to HDFS. We will actually achieve the end-to-end semantics with Kafka streams and Kafka Connect. We have already some KIP is basically an improvement proposal inside the Apache Kafka community. And if you're interested, take a look at our wikis and its ongoing design and implementation work.
So you showed a program where you are setting up a various streams and processing, and saying this might be what this might be what this processing is doing on it. And I thought I heard you say something along the lines of you're going to start up two of these programs that define the same, or two copies of the same program that define the same set of streams. The fact that they're both running means they'll work together to make all this happen. That's the way it works?
I think, I mean, if I don't understand it wrong, your question is that how you achieve data parallelism with multiple instances of Kafka streams?
Yes. So what you're saying is that if I were going to use this, I write my own Java program that describes streams the way that you showed.
Yeah.
And I make two jars of the same program, and I just run them both?
Exactly. The question is that how you actually run multiple instances of your Kafka stream library, and the answer is whatever you like, right? You can just run different processes, the same piece of code as a Java application on multiple processes, even across different machines. The library will handle the automatic load rebalancing among those clients. And you can deploy such a application using as simple as a WAR file, or you use whatever your favorite deployment tools to do that.
Using this thing like a database. So the same program that is capable of implementing the streams and is basically one of these peers can also say, and tell me the value for that key, and pull a row out of that table.
That's right. The question is that, again, this is why you have backup slides. The question is that, can you actually query your state stores? The answer is yes, in the future. And it's also an ongoing work that we are actually implementing currently. And the goal is that for any of your state stores in your Kafka Stream instance, you can actually query it outside of the Kafka application to basically get a current snapshot of your image of your stores. Actually, can I just answer maybe another question from another person?
Where stay, right? Do you stay locally or you go to some centralized? Do you stay locally? How do you deal with that?
So the question is, for local states, how you actually deal with fault tolerance when it crashes. So as I mentioned in the fault tolerance slide, the way you do it is that when you crash and the whole process is being automatically migrated into a different instance, you can actually restore your states from the changelog topic.
How do you restore state? The state is local.
I mean, the state is local, but that state can be locally restored from the changelog topic, right? Recompute or restore.
Recompute and restore.
Restore, not recompute. You don't really need to recompute again.
But if restore in that particular local state has been crashed and kind of erased, how do you restore?
So imagine you have a write-ahead log, right? You can always replace the write-ahead log to restore your states.
That write-ahead log has been crashed.
No, it is in Kafka, and Kafka is highly scalable and persistent.
Oh, so it's centralized.
Yes, it's centralized in Kafka, and because Kafka uses replicas, so that your changelog will not be crashed.
So you store your state in Kafka.
You store your state in your Kafka Streams client, but the changelog, which is the write-ahead log, is stored in Kafka cluster.
So it's still a state in Kafka. It's the same thing. It's the same thing. What I mean is the same thing. Yeah. Change log is just a state.
Okay, so one summary is that the Kafka streams runs on client side, and the Kafka cluster may run actually on different machines. Your store co-located with your Kafka streams client, but your changelog belongs to Kafka cluster. Yes?
So are you two questions. Are you advertising K-table as a source of truth? Second, Kafka is designed to have interdimensional time, not have infinite dimension.
Yeah.
So if you're going to restore for fault tolerance, if you're going to use stream capture log, it's possible that you have run out of your memory.
So the first question is are you going to put K-table as your source of truth? The answer is the K-table is actually, again, as a materialized view of your underlying streams, right? So the streams should be your source of truth. And your table will just be like a snapshot or running view of the stream. The second question is, okay. So the question is how you actually guarantee that your changelog will not like grow indefinitely. We use the log compaction feature, which is like a Kafka server feature, so that we can actually compact old key value pairs that has been overwritten by the new key value pairs. So that as long as you keep updating and your state store space is limited, you won't actually have ever growing changelogs.
Will you upload your slides?
Sure. I think it's in Kafka Streams. I mean, the Hadoop Summit will do it.